So the next thing we need to do is what? Get some boundary conditions. So there's our solution. Made you write it twice, I guess. So let's first think about a boundary condition where we have two constants that are unknown. So let's think about our first boundary condition. We need a boundary condition somewhere out here, and we need a boundary condition at the other end of the domain at r equals 0. This boundary condition here maybe is a little hard to see, but what has to be true at r equals 0 in terms of heat flow? Set it right there, right? It's 0. There's no place for heat to flow once you get to the 0 coordinate in the radial direction. So our boundary condition at that, say, infinitely small control surface that we've drawn up there is that q dot has to be equal to 0. So we'll write that out here. Q dot at r equals 0 is equal to 0. All right, so let's work on that one a little bit. Introducing our rate equation, we would say then minus k 2 pi rl dt dr evaluated at r equals 0 is equal to 0. You can simplify this out with the constants and just say r dt dr is equal to 0. So this is all at r equals 0. So this is furthermore saying 0 times dt dr is equal to 0. This is a little tricky because now I'm taking something, a dt dr, I could put in the expression for temperature if I wanted to, take its derivative. But the problem is I'm multiplying that whole thing by 0, right? Because I'm evaluating this at r equals 0. So what is that actually saying? That's saying, well, this is true pretty much for any value of dt dr, so long as dt dr is defined. The only possible way that this doesn't work is if dt dr is infinite. Okay? So this has to be defined, right? That means not infinite. So let's think about that or look at that a little bit more closely. So let's take dt dr. Let's take the differential of our temperature expression that you see above here is actually given right here. All right, so dt dr, if I substitute in r equals 0, I'm going to say minus g dot triple prime times 0 over 2k plus c1 over 0. That's from our dt dr. What has to be true in order for dt dr to be defined? Yes. All right. So from this boundary condition, through kind of this weird logic, we decide C1 is 0, and that's it. Right? So in order for this problem to be defined, in order for us to get a useful solution out, C1 has to be 0, and that's enforcing the first boundary condition. We're done with that first boundary condition. Okay? All right, so the second boundary condition's maybe more straightforward or more physically meaningful. So here we're taking a control surface. It's a little hard to see. But at this boundary, at the outer edge of the hay bale, right, not at the plastic, at the outer edge of the hay bale, which is the edge of our domain, I'm going to draw an infinitely thin surface, and I'm going to say what's going in and what's coming out, and that's our boundary condition. So we have, at the edge of the surface, we have then conduction through the plastic, and then we have convection to the surroundings, maybe radiation to the surroundings. And the surroundings are at a known temperature, but we don't know anything about the actual like temperature or heat flux at the boundary. So we basically have to write our boundary condition this way, and then substitute in equations and get something in terms of the things we do know. All right, so let's write this out. Our boundary condition at r equals r out is q dot at r equals r out has to be equal to, we'll call it q dot out or q dot surroundings or something like that. It is just the amount of heat that's leaving due to convection radiation. So what would my expression be for q dot out? Well, q dot out would be something like t at r equals r out minus t, what was it, t infinity divided by the total resistance, which I said we had. If you go back to the problem statement, you'll see we have conduction across this plastic and then convection. That was the only thing we were given. So that would be the sum are, let's see, where am I? The sum of the resistances, which is our conduction plus our convection. Right, that's our rate equation for what's leaving, assuming that we have that temperature T R equals R out. Q dot R equals R out, we can just use Fourier's law evaluated for that position in the domain. Okay, so if we do that, we end up with this expression. So Fourier's law would say minus K 2 pi RL dt dr evaluated at R equals R out has to be equal to this thing up here, which is, I'll just rewrite it, T R equals R out minus T infinity over R conduction plus R convection. Right, R conduction being the conduction through the plastic. Okay, so this is actually our boundary condition. We're still not done, though. We still need to say this dt dr at R equals out. We have to substitute that in, and we have to substitute in our temperature using the equations at the top. Okay, so let's see. Before we do that, let's get some expressions here for these guys. So we need to know the conduction through the plastic and the convection. So the resistance due to conduction through the plastic. All right, so our conduction plastic is going to be, it's a thin enough surface. You could probably use a plain wall conduction resistance if you wanted to, but just for the sake of being entirely correct, let's use the actual formula. So we say ln of the outer radius, which is R bale plus the thickness of the plastic, divided by R bale. Right, so the log of that term divided by 2 pi k of the plastic L. That's our plastic resistance. The convection is going to be, let's see, hopefully try not to run out of room here. So our convection is going to be 1 over h bar times the area, which is 2 pi R bale, I'm running out of room, plus thickness times L. Hopefully you know what I mean there. So it's just H times A, right? We're just taking the outer area. Okay, so we have those two things now. And then we could go back and substitute in our temperature. Let's see. So I think, you know what, we're at this point. What you would do is you would take this temperature, evaluate it, substitute it in. I kind of wanted to get to the ease example and just show you that. So let me do that. I think we're in pretty good shape with understanding this. So, but you have all the pieces you need here, right? We're just substituting in the temperature dt dr and evaluating it at the right R. All right. So let me move over here.